So the next speaker is Jim Oliver, again from Oxford, and there'll be thin film flows.
Can everyone hear me? Is the speaker working? Can everyone hear me okay? Great. So thanks very much for the organisers for the invite. I'm going to talk about thin film flows with mass transfer. Quite a few people have been involved on this project for a number of years. So the experimentalists are Morgan Alexander and Siggy Rodson. Morgan's at Nottingham and Siggy's at KAUST. But I'm not going to give much of the experimental data today. I'm going to focus on the simplest possible model for the effect of mass transfer on the contact line dynamics of a droplet. So Matt Saxon's the PhD, well, the DPhil student who's done a lot of the asymptotics in this talk, in collaboration with John King and myself. John Whiteley, who's in Comp Bio at Oxford, did a lot of the numerics, which was a real sledgehammer affair with the finite element method. So I'm not going to tell you much about the numerics, but needless to say, he was very careful about convergence and so on. And then Dominic Vell has been involved and been very especially useful with the numerics. My talk's going to go a very brief slide on the motivation. I'm going to give you the dimensionless model problem, and very similar equation to the ones that Barbara was telling us about this morning. But I'm going to build in the simplest model for contact line motion and the simplest model for mass transfer that I can think of. And then I'm going to do the small slip asymptotic, so the model I'm going to choose to regularise the contact line singularity is slip. That's the simplest one, but a lot of the asymptotics I do give you generalisations of Tanner's law that are universal. So you could change the regularisation, but you'd still get the same answer. So I'm going to look at the small mass transfer rate and the large mass transfer rate, and I'll tell you precisely what I mean by those two. And in each case, I'm going to do the small slip asymptotics, describe briefly the resulting droplet evolution at leading order and show some fairly good agreement with the numerics, and then I'll try and wrap up by discussing what this means, and then tell you a little bit about what we're doing currently. So the original motivation for this problem, from my point of view, was looking at the evaporation of droplets that were about 100 picolitres on a substrate. So about 20 to 30 microns in size when you dose them onto the substrate. And the substrate that the experimentalist was interested in was one in which there was a gradient in wettability and a gradient in chemistry in two different axes, and he wanted to know where cells were most happy. So he wanted to measure the wettability, and because there's a gradient in wettability, he had to dose the substrate with a small drop. Because the drop was small and he didn't have the humidity quite right, the droplet evaporated. And as it evaporated, it went through the full contact line motion. So it would spread, get pinned, retract, and then disappear. So what he found was that if he took the first frame of his video, that would give you very good correlation with the static water contact angle that you would measure if you were to do a static experiment. And so that's the frame that he used in his experiments, and he showed that it did quite a good job, but he would quite like to extract more information about the contact line law from the full dynamics of the evolution. So that's where we got talking a long time ago. So John King originally worked on this problem for looking at biofilm type problems, where people write down thin film type models for growing biofilms on substrates. And so this kind of gives me I don't have to worry so much about the size of my evaporation rate. I'm allowed to have evaporation and condensation rates that are much higher than you would typically see for a water droplet or something else in our atmosphere. So I can, because I've got a biological motivation in which the dimensionless parameters are completely different, I can pretty much make up my dimensionless parameters. So typically, people have looked at evaporation and condensation of sessile drops because they're important in a number of applications which are listed here. It's a complicated free boundary problem because you have to worry about transfer of mass, momentum and energy in the liquid, in the atmosphere around it and in the substrate. For partially wetting drops, the free boundary problem is compounded by the fact that you've got a singularity at the contact line. So there's a large modelling literature dominated this topic, and typically it's numerical simulations in a thin film limit. and it's very much focusing on doing a systematic dimensional reduction of the Navier-Stokes equations combined with numerical simulations and comparing that with experimental data. So our focus here today is going to be slightly different. We're going to look at the simplest possible model for mass transfer, the effect of that on the simplest possible model for contact line motion, and we're going to do the small slip asymptotics. And that's going to be pretty much the whole talk. And this builds on work, this builds on work by Anderson and Davis and Hocking. So some of the inner regions they wrote down I've got in this talk, but they never put it together the way I'm going to tell you about today. So I deleted all my slides on deriving this dimensionless problem because of Barbara's talk. So suppose we have a two-dimensional blob of viscous fluid with constant surface tension lying on a substrate. H is the thickness. I'm going to do the symmetric problem in which the blob lies between 0 and S. S of t is the a priori unknown location of the contact line. So this is the thin film equation that's going to be the subject of this talk. If n is equal to 2, I've imposed a Navier slip condition on the substrate. If n is equal to 1, then I've written down one of Greenspan's models. Provided this slip coefficient n is less than 3, I'm going to get contact line motion. So provided n is less than 3, I've relieved the contact line singularity and I can get motion of my contact line. Lambda is my small parameter. Lambda is the slip length. That's why I've got a 3 minus n here and an n in here. If you're not comfortable with this generalized slip law, just set n equals 2 in there and ignore any other value of n. We did the leading order asymptotics and found that the leading order solution is independent of n for n less than 3, and numerically it's convenient to choose n equals 1 when you're using the finite element method. So that's my thin film equation. I'm going to assume that x equals 0 is a line of symmetry, so I have 0 slope and 0 flux. At the contact line I have 0 film thickness. I'm prescribing a finite microscopic contact angle, so that's minus hx equals 1, and then I have no flux of liquid through the contact line. So of course I have 3 boundary conditions here because I need to determine the location of my contact line S of t as part of the problem. I need to prescribe an initial condition for h, and I'm going to choose my initial droplet width to be 1. This is a dimensionless problem, and so in this problem I have 3 parameters, lambda, j and n. Lambda is a slip length. J is going to be the rate of mass transfer. If j is positive, this corresponds to evaporation and I'm losing mass. If j is negative, then that's condensation, I'm gaining mass. If j is 0, I'm back to the usual droplet spreading model. So I struggled to write down a simpler model of this than this that had contact line motion and mass transfer in it. So in more complicated models, you might worry about temperature effects, Marangoni, vapor recoil, gravity, the transporter of vapor in the atmosphere, which would give you a non-uniform constant J, but I'm just going to look today at the case where my mass transfer rate J is just some constant. Okay. Because I have no flux through the line of symmetry x equals 0 and through the contact line, the total the half cross-sectional area of my drop, which I'll denote by little m, obeys this differential equation when I integrate the thin film equation from 0 to s. So I'm losing mass at a rate proportional to j times the length of the half drop, and then this capital M is my initial area. Okay, so this is the thin film equation I'm going to work on, and I'm going to do the small slip asymptotics and tell you what happens for different size of j. Okay. So I'll tell you what happens, or I'll remind you what happens when j is 0 on the way through. So let's start with the small slip asymptotics. When j is small, so the relevant distinguished limit is the so if you have no mass transfer, the time scale for motion of the contact line is log 1 over lambda. So the droplet moves on a very, very slow time scale, and so I'm going to look at the distinguished limit first, in which the mass transfer, the mass loss, is on the same time scale as the contact line motion when there's no mass transfer, if that makes sense. So the relevant distinguished limit is the one in which the mass transfer is order 1 over log 1 over lambda, and the reason why it depends logarithmically on the slip length will drop out from the asymptotics. So if j is 0 and n is equal to 2, then Andrew, guy sitting just here, and Hocking, so Andrew showed it first in 1982 and Hocking showed it in, using a slightly different asymptotic method, which I'll use in 1983, showed that the contact line motion is on this slow time scale as lambda tends to 0, and the asymptotic structure comprises three regions: a quasi-steady outer region on the length scale of the drop, an inner region on the length scale of the slip length, and then an intermediate region in between the two, in which the slope is a slowly varying function. And then matching between the outer and the inner gives you Tanner's law. So remarkably, what we find is that if we have constant mass transfer, and for any n less than 3, then this same asymptotic structure goes through. So I'm considering the distinguished limit in which curly j, normal j is equal to curly j over log 1 over lambda, as lambda tends to 0, and that's the relevant distinguished limit. So for a water droplet evaporating on a substrate, this is a very, very large evaporation rate. But for things like biofilms and so on, where you might write down this model, this might be appropriate. So a quick whip through the asymptotics. In the inner region, the length scale is order the slip length, the film thickness is order the slip length, and we get this quasi-steady ODE describing the evolution of the film thickness. These are my boundary conditions at the contact line, and then to match with the outer via the intermediate, I need my slope to be finite as x goes to minus infinity. So in here, delta is another small parameter which is related to lambda by this relationship up here. So 1 over delta is my time scale of motion. So the solution to this problem is simply h naught is equal to minus x. So in the inner region, the condition that your microscopic contact angle is equal to unity fixes the droplet to be fixes the region to be a wedge-shaped region. In the outer region, because the time scale of evolution is long, you end up with a quasi-steady problem, in which the curvature is constant, so you end up with minus hx, we end up with hxx equals minus p naught, where p naught is the pressure. This is my symmetry condition on the line of symmetry, and then at the contact line, which I'm denoting by capital S naught on this in this small evaporation regime, I have minus dh naught by dx is equal to capital theta naught, and this is the macroscopic contact angle. So here p naught and theta naught are macroscale variables that need to be determined. I can integrate this up to get the film thickness in terms of p naught, and then p naught in terms of the macroscopic contact angle theta naught. And then if I plug these into the global conservation of mass condition that I had a couple of slides ago, I get an ODE, the first ODE relating the width of the drop to the macroscopic contact angle. So of course the macroscopic contact angle, let me go back if I can, is the angle that you measure on the outer length scale in comparison to the microscopic contact angle, which is equal to unity, and that's the contact angle you measure on the inner length scale. So that's our first ODE. To get our second ODE, you need to scale into the intermediate region between the two, and in this region the slope is a slowly varying function of psi as defined up here. So if you make this scaling in here, then you end up with this quasi-steady problem dropping out of your thin film equation. So your fourth order nonlinear PDE becomes a first order ODE. In the absence of mass transfer, this curly j is equal to 0, and when you match with the outer region, you get this matching condition, because k naught is the leading order slope, and when you match with the inner region, you get this matching condition. So you've got a first order ODE for the slope inside this intermediate region, which describes the slow variation of the slope as you go from the outer into the inner. So the solvability condition for this boundary value problem, so we've got a first order ODE with two boundary conditions, the solvability condition gives you the contact line law in the form the velocity of the contact line S naught dot is equal to some function of theta naught and the mass transfer rate. So if this curly j is equal to 0, you get Tanner's law dropping out, which I'll remind you about in a second. So in summary, the outer problem selected as lambda tends to 0 is quasi-steady, and the problem reduces to an initial value problem for for two macroscale variables, so your contact line, the radius of your drop, capital S0, and your macroscopic contact angle, theta naught, and you have two ODEs to solve for S0 and theta naught. And I need to tell you about this contact line law in a minute and what it looks like. So to get the right initial conditions, you have to match with a short time evolution on a rapid time scale, so on an order 1 time scale, in which your initial profile relaxes to a parabolic profile, one of constant mean curvature, and that's straightforward to do, and that gives you these initial conditions on S0. So on this rapid time scale, all that happens is that the free surface relaxes under surface tension, the contact line doesn't move at leading order, and no mass is lost at leading order because mass loss is small in this regime. So we have these two initial conditions. If J is equal to 0, you get this contact line law. The velocity looks like theta cubed minus 1 over 3, and this is just Tanner's law. So this law up here generalizes Tanner's law to take into account uniform mass transfer. And this is provided your regularization of the contact line singularity is on a length scale that's small compared to that of the drop. This contact line law is universal in the same way as Tanner's law is universal. It doesn't matter whether you use co-joining, disjoining and a precursor layer, or whether you use slip, you get the same answer. So what happens when you put mass transfer in? So this dotted line is Tanner's law, where the velocity of the contact line is a cubic function of theta naught, the macroscopic contact angle. So this is the contact line law that drives you back towards the equilibrium of unity. If you have condensation, so J is negative, then the contact line law is Tanner's law is just shifted up a little bit. However, if you have mass loss, then a singularity appears in the contact line law. You have a simple pole in Tanner's law appearing for J positive. And in fact, the normal velocity looks like minus J over theta naught, as theta naught tends to naught plus, or J tends to minus infinity. So our Tanner's law ends up being modified to this kind of shape. So it's going to the drop's going to behave pretty much the same as if there were no mass transfer, until the angle gets very, very small, and we're going to start to see the effects of this singularity. Okay, so I was quite surprised to see this singularity cropping up when you just put in even a simple model for mass transfer. So in the absence of mass transfer, you can integrate up the conservation of mass and Tanner's law, and you find that theta tends to 1 and S tends to some constant that depends on the initial mass that you have, and so the droplet just relaxes back to an equilibrium state. So that's shown here. So the key point here is that if the drop is the radius is small, then it'll spread, and if the radius is large, it'll contract to its equilibrium. So when you put in mass transfer, you find there are 3 regimes, and the way you see that is to note that theta dot is positive, 0 or negative, depending on whether S dot is less than, equal to, or bigger than minus 3J over twice theta naught. Just by rewriting the global conservation of mass condition in this form. When you do some plotting, you find that this contact line law can intersect this critical curve either once, twice, or not at all. So if there's no intersection between my contact line law and this critical curve, then theta dot is always negative, and my droplet always shrinks to 0 without spreading first. If in the second regime, if there's 2 intersections between these curves, the contact line velocity can be negative, positive, or negative, depending on what the angle is. And in the case of, well, this is typical for the case of condensation, if there's only one intersection point, then you get something which looks very similar to the Tanner's type law. So these regimes occur for, this regime occurs for J less than naught, curly J. This regime occurs for a finite window of J, and this regime here occurs for J sufficiently large. And you can work out using elementary calculus where those regimes are. So in this diagram, I've got the mass transfer rate plotted as a function of my angle. In regime 1, theta is always decreasing, theta dot is negative, and theta goes to 0 near extinction. In regime 2, my angle tends to some finite value that we have a prediction for, and then in the condensing regime I get something similar here as well. so let me just show you the kind of things that, the kind of evolution you get in each of those three different regimes. So the thing that I found interesting is that you have, you'd have thought the way in which the droplet evaporates would be universal. You would have thought there would be a unique power law that describes the kind of behaviour as it evaporates. And what we're seeing here is that there's a possibility of a different kind of scaling behaviour depending on your initial conditions. So in regime 1, when theta always decreases, you find that both theta and the contact radius go to 0 at the same rate. So you can do the numerics of the ODEs, and then you find that you get this square root scaling behaviour in theta and s as near the critical extinction time, well, near the extinction time, capital TC. So this 1.5 power has been seen quite a lot experimentally. For water, it tends to be about 0.6, but no one really understands the reason why that's the case. But for other liquids, half is what they tend to see. So that's regime 1. That's very rapid evaporation. Regime 2 is slightly slower evaporation, and if you choose the right initial condition, you can get onto, you can tend to this stable branch here, and what you find is that near extinction, the angle tends to oh, sorry, this is very frustrating. The angle tends to a constant, and the droplet radius shrinks linearly. And then you see a very similar kind of condition, kind of behaviour in the case of condensation. So if you're supplying mass to the drop, you find that the angle tends to some constant value, and the droplet expands with, well, its radius goes linearly for large t. So that was the predictions for the small slip asymptotics, and John did some, well, he basically hit it with a sledgehammer. So he had a non-uniform grid. We did slip length of 10 to the minus 5. He had about 200,000 grid points. He put 100,000 within a ridiculous distance of the contact line, and then I made him do a load of convergence tests, and everything was okay. And for such a small slip length, we see very good agreement between the asymptotics and numerics. The dotted line is the asymptotics I've just described you, and the solid line just on which this dotted line lies is the thin film numeric. So this is the width, S, this is the mass, and this is showing profiles with different time steps. So for small enough slip length, the asymptotics agrees with the numerics. So this is no mass transfer. This is regime 1 where you get a square root singularity. This is regime 2 where it seems to go where it does go linearly, and then regime 3 where you're condensing and the droplet is expanding and growing in size. So we also plotted extinction times. So solid is the ODE model, and these dotted lines are numerics. This is for a slip length of 10 to the minus 5. And one interesting thing we did find, and there was a range of curly J over which there appeared to be an instability in which the contact line couldn't keep up with the bulk of the drop, and the droplet would actually touch down in finite time and appear to want to form a rim. So this doesn't. Well, it would be a rim in the axisymmetric version of the problem, but obviously that's not true it would be just a straight line in the 2D version of the problem. And locally near this point here, it looks like a parabola moving down with constant velocity. But we have no good theory as to why you're getting this pinch off at these intermediate values of the density. So that was one particular surprise coming out of this asymptotics. So I'm running out of time. So I can't tell you the whole story for the small slip asymptotics with large evaporation rate. But let's just, so the two things I should say, I guess, is first of all, the asymptotic structure is much simpler than in the small mass transfer case. There's just an inner and outer region. In the inner region, on the length scale of the slip length, you end up with a much more complicated inner problem. So in the small mass transfer rate, my speed of motion of the contact line and my mass transfer was small, so I had 0 on this right-hand side, whereas here I have both of these terms, two terms coming in. So the key question is this problem correctly specified, and is it possible to match with the outer solution in which the slope is growing linearly as x goes to minus infinity, and little theta naught here is once again my macroscopic contact angle. So you can answer that question by doing a local and far field analysis, and I'll just whip through these slides. So as capital X goes to 0 minus in my inner region, that you find there's 1 degree of freedom. I can't press this button. You find there's 1 degree of freedom in the local expansion of H. If you go into the far field, the first thing you find is that you can only match with the outer if S dot is equal to minus J over theta naught. That kills this, this term here. And so this is essentially a matching condition with the outer region that generalises Tanner's law, and this dovetails nicely with what we saw earlier on with the small mass transfer case. So that's the first thing that drops out. The second thing that drops out, and let me gloss over the details, is that by doing a local and far field analysis, what you find is that the form of the outer problem that's selected in the small slip limit is completely different depending on whether J is positive or negative. So for both cases, you get the nonlinear, the full nonlinear PDE, but without any slip. For J positive, you have this contact line law that I just alluded to. S dot is equal to minus J over theta naught. But for J negative condensation, the inner problem demands that theta naught is equal to 1. So if you're adding liquid, you have to add it in such a way that the macroscopic contact angle is equal to unity. If you're pulling liquid off, you have to solve for the macroscopic contact angle as part of the solution to this full outer problem. So evaporation is a genuine free boundary problem, whereas condensation is a moving boundary value problem because I know the location of my contact line in this regime. So we did some, well, first thing we did was look for some similarity solutions. You can find a type 1 similarity solution for condensation, and that appears to be the global attractor when you compare it with the full thin film numerics. This dotted line here is the type 1 similarity solution. Interestingly, there's no type 1 similarity solution for the evaporation case. We couldn't find a solution of this nonlinear problem. However, there is an exact solution which just corresponds to an inverted parabola moving down with finite velocity. And this guy seems to be the local attractor, and this is a plot of the full thin film numerics v this exact solution, and they lie bang on top of one on top of the other. And if you choose different initial conditions, you find that the exact solution appears to be the global, well, the local attractor near extinction. So you get back to a square root behaviour. So in summary, the contact line law that you select as the slip goes to 0 is extremely sensitive to mass transfer. If J is negative in order 1, you get a finite velocity and liquid is just added to the contact line. If J is small enough that it competes with the hydrodynamics of contact line motion, you get a generalization of Tanner's law. If J is sufficiently large and positive, you get S dot looks like minus J over theta naught, and you can do the asymptotics to go from one regime to the other. So you should really view Tanner's law in this generalized Tanner's law as a way of, as kind of like a boundary layer in variation of this parameter. So that as you go from J being negative to positive, you go through this evolution according to Tanner's law. And I've already said that about what happens to the outer PDE. So for the small mass transfer case, you have a quasi-steady PDE, but for the large mass transfer case, you have the full PDE without slip. There's good agreement with numerics, although there's some outstanding issues that we're not sure about, like touchdown. And let me just finish by saying we're currently applying these ideas to more realistic 1.5-sided models for droplet evaporation, where you have vapor recoil, gravity, Marangoni, and a simple model for the transport of vapor density. And the most interesting thing that came out of this analysis, if you throw away everything except so if you cross off all of these terms and you look at the large kinetic Peclet number limit, you find that the droplet shrinks like Tc minus t to the 8/15ths over the time scale of motion. But our collaborator doesn't think he can find a difference between a half and 8/15ths. But well, if we get enough decades, we might be able to. I'd better stop there, I think.
One very quick question.
You mentioned that it didn't matter whether you used a slip hypothesis or a more complicated one that involved mass transfer.
So if the local physics you choose is independent of the rate of mass transfer, that's true. But if there are different regularizations in which you regularize the singularity in the evaporative flux and the contact line and in the contact line singularity in the same in a region, then this wouldn't hold. So provided my regularization happens on a large length scale than the slip length, or whatever regularization I choose, the generalized version of Tanner's law that you get is going to be universal.
You didn't wait for me to ask a question.
Sorry.
I mean, are you being consistent between the mass transfer that takes place on the large scale, because you're either evaporating or depositing, and the mass transfer, which is many people would think is the most likely physical solution of the compact line mechanics?
I don't. So, in which bit of the model, which equation do you not like? Because I don't understand.
Are they consistent? I'm just simply saying, would they be consistent?
So we spent quite a lot of time talking to John Wetlaufer about this kind of modelling, and he was content that you could get this kind of thing. But I don't understand. The aim was to write down the simplest possible model, and if you tell me,
all the mass fluxes balance up from your different regions. They all.
Oh, of course they do. Yeah.
Is that what you're really asking?
Well, you have to put in. Sorry, it'll go on too long.
I think you could change you could even change the small scale angle and do the same analysis again, couldn't you?
Yes. Yeah.
Right. Probably should move on.
Yes.
You can grab them over a drink or two.